Так, прошу прощения за задержку, я запутался с аккаунтами. Вот, поэтому не сразу смог запустить конференцию. Так, что-то я не слышу никого опять сейчас.
Здравствуйте.
Попробую.
Здравствуйте.
Так. Скажите кто-нибудь, чтобы я послушал еще раз.
Здравствуйте,
Ага,
слышно?
опять не слышу. Так, ну ладно. Еще раз скажите, попробуйте.
Здравствуйте, слышно?
Вот теперь слышно, да. Все, так, сейчас иду, открою. Так, значит, окей. Today, I will present a smart algorithm to decode Reed Solomon plus Adamar code. So Reed Solomon plus Adamar, a smart algorithm for list decoding. First of all, let's recall what this code is. We consider a Reed Solomon code with parameters 2 to the n. So we choose small epsilon and consider polynomials of degree epsilon times 2 to the n. So the number of the dimension of the code is that plus 1, and the distance is 1 minus epsilon times 2 to the n, and the alphabet is 2 to the n. And this will be the outer code, and as inner code, we consider a version of Adamar code where we consider not all linear functions, but those not all affine functions, but only linear ones. So we assume that the constant term is 0. In this way, we lose half of the code words, so the dimension will be n, the code length will be 2 to the m, and the distance remains intact, 2 to the m minus 1. Actually, there is no consensus in the literature what is Adamar code. Some authors call this code Adamar, some other code the Adamar code, the code where the dimensions are m plus 1 and one considers all the linear functions. So anyway, when we concatenate these two codes, we obtain a code with parameters two to the 2 times m, epsilon m 2 to the m, actually plus 1, but we skip this plus 1. It's not important to us to simplify the notation. And the most important thing here is the relative distance. So the relative distance is 1 minus epsilon over 2. So this is almost the maximal relative distance possible for binary code. So by Plotkin theorem, the maximal possible is 1/2. And if epsilon is small, this is close to 1/2. Times 2 to the 2m. So the block length is 2 to the m, and the distance is 1 minus epsilon of that. And by Johnson bound, we can list decode this code from that many errors. We can decode from 1 minus square root of epsilon 2 to the m errors with list size two times 2 to the m. And now I want to explain how to do that in polynomial time. Actually, we will decode from a little bit less errors, and the list size will be not 2 times 2 to the m, but square root of 1 over epsilon times 2 to the 2m. But it's not important. So the theorem we will prove today will be the following. There is a polynomial time algorithm to approximately 1 minus square root of epsilon over 2 to the m, square root of 1 over epsilon 2 to the m, list decode. So this is the number of errors we correct. This is the size of the list. Decode that code, Reed Solomon plus Adamar. And the algorithm will be a very smart one. So usually when we list decode, so when we decode Reed Solomon, we always solve in the beginning system of linear homogeneous equations, find certain polynomials, and then factor, and then either divided polynomial by something or we factor them. And here we will do the same thing. So when we just list decoded Reed Solomon, we constructed a polynomial R of 2 variables of small k degree. So let's recall the notions which we used when we considered an algorithm, a fast algorithm to list decode Reed Solomon. First of all, we considered polynomials of 2 variables where the ground field has 2 to the m elements. So 2 to the m is the field used for Reed Solomon code. And we called it k degree. So k will be the, recall that the messages in Reed Solomon are polynomials of degree, of certain degree. In our case, the degree of polynomials is at most epsilon 2 to the m. We will denote this by k. So k is epsilon 2 to the m. And that is the degree of polynomials in the first code, in Reed Solomon code. And and we call k degree of R is defined as follows. K degree of each monomial is equal to the degree of x plus k times the degree of y. So the degree of a to the I, x to the I times y to the j is equal to I plus k times j. So to say y is k times more valuable than x. And the first step is to construct a polynomial of small k degree that passes through many points on the plane. And more specifically, it has certain points are roots of that polynomial of large multiplicity. So let's recall again. So we call A, B is a root of R with multiplicity, say M. If the polynomial R of A plus X, B plus Y has no monomial of degree of normal usual degree less than M. So the first step will be to find a certain non-zero polynomial which has many roots. Now we need to explain what roots we want to have that polynomial. So step one. Let's first recall the lemma, which was almost proved in one of the previous classes. So assume that in this lemma, we will consider the plane where here are elements of the field on one axis, and on the second axis, we have also elements of the field. And for each point, call it say x, y, we assign certain number a, x, y. This will be a natural number. This will be a desired multiplicity of that root. And the lemma is the following one. Let's call it, say, okay. If the sum, assume that the sum of all multiplicities times multiplicity plus 1 over 2 over all possible x and y in the field is smaller than certain d squared over 2k, then there is a non-zero polynomial R of xy of k degree less than d, such that each xy, each pair xy is the root of R with multiplicity A of xy. And how we prove this lemma? The sketch of the proof is the following. Each requirement for each xy, we have one requirement that point, that pair is the root of the polynomial. That requirement can be expressed as the constraint about the coefficients of the polynomial. And this constraint is naturally written as a homogeneous polynomial, as a system of homogeneous equations where the number of equations is the number of monomials of degree less than d. Monomials of degree less than a of xy. And the number of such monomial is that binomial coefficient. So a of xy, choose 2. And we sum up over all xy, so we obtain the total number of homogeneous equations we have. On the other hand, the number of coefficients in such polynomials is strictly larger than d squared over 2k. So we have proved that once. And so this inequality, this assumption, guarantees that the number of coefficients of R is strictly larger than the number of homogeneous equations of such a polynomial. And so this guarantees that there is a non-zero solutions to that system, a non-zero solution to that system. And that solution provides coefficients of the third polynomial R. So this is a sketch of the proof, so I won't repeat that proof. We used that lemma actually, and also we proved that lemma in the case where all these R's are the same number. But now we need that lemma in the full generality. And so the first step, on the first step, we use that lemma for some particular coefficients. So for some particular A's. So what will be choose as A's? So first of all, so recall what do we want? We had some unknown polynomial p of x. So this is the message. So how it is decoded? First of all, we consider the value of that polynomial p of xi, where xi ranges over all the elements of the field. This is how the Reed-Solomon works. So this will be the encoding of our message. And now each of this number is actually represented as sequence of m bits. And that sequence is encoded by a long string of length 2 to the m. So each sequence of, so this value is considered as m bits. Each value is considered as m bits. Those bits are considered as coefficients of a linear function over from f2 to the m to f2, call it say f, and we evaluate this function in all possible points. So each of these values using Reed-Hadamard code then is encoded by a sequence of 2 to the m bits. So this is how our words, our code words. Now, what do we have? We, instead of, so let's write this. So this is our code words. It has 2 to the m, 2 to the m, 2 to the m, and the total number of blocks is also 2 to the m. So these are bits. This is Hadamard encoding of piece values. Now, instead of this guy, we receive something different because some of the bits are corrupt. And so instead of these genuine encodings of values, we obtain something else. And call these blocks by Z1, Z2, Z to the M. So now I will explain what we will use as multiplicities of our rules. So this is 2 to the M, this is F2 to the M. So this point will be just considered as one of xi, xi's. And this one will be considered as a possible value of that polynomial. So in this picture, our polynomial can be represented as a line, as its graph. Y is equal to P of X. Now, we consider this point as possible root of our R. And our multiplicity will be defined as follows. First of all, consider the value B of X, Y, which is the Hamming distance between Z, the corresponding Z. So let's call this Xi and this Yj. So this is Xi and this is Yj. So, and then the multiplicity, which will be denoted by Aij, will be the following one. First of all, consider the following number, Bij, which is the Hamming distance between Zi, so what we receive through our channel. So this is a 2 to the M bit sequence. And the code of Yj. We just compare what we receive with the code word of Yj. So we do not know each code word actually was there in the beginning. So because it's spoiled somehow. And so we compute the Hamming distance between what we receive and all possible code words which could be here. So here, imagine that here is the I, and here we had a now unknown code word code of Yj. So this is known to us, but this is not. So we consider all possible code words, and for each code word and for each number of block, we consider this number. This is a natural number. And using this number, we compute multiplicities. The multiplicity will be the number of equal positions in these two code words minus the number of different positions. In other words, it will be the total length of those words 2 to the M minus 2 times the Hamming distance B of Jy. And so if this, recall that our multiplicities should be non-negative or better even positive. So if this is positive, then we will take as multiplicity. Otherwise, we will take just 0. So either this is the multiplicity is set to this number if positive, and 0 otherwise. Так, ну я уже чувствую, что люди перестали понимать. Скажите, понятно, как определяется вот это вот? Как, получив
Да,
испорченное это самое кодовое слово, мы вычисляем вот эти кратности.
да, понятно.
Okay. So we compute these multiplicities, and then we just find d such that minimal, maximal d, no, sorry, minimal or maximal, minimal d, such that we can apply our lemma. So recall our lemma. If the sum of all multiplicities, in our case, so we have a new notation, if the sum of aij times a of ij plus 1 is less than or equal to d squared over k, then we know that there is r of degree, of k degree, there is such r. And we just set d to be square root of k times this. So we set d equal to square root to this sum times k. Recall that k is the degree of k is epsilon 2 to the m, is the degree of our message. And we set that d and find r of xy such that it satisfies our lemma. This is the first step. So on the first step, we set such d and find such r. Now, the second step. Now we want to show that if the number of errors is small enough, then our polynomial p is the root of r. So on the first step, we will want to show the following lemma. If the total number of errors is less than certain value, then r of x, p of x is 0. So why is this? First of all, we need to find, of course, this bound, but let's start with the proof and we will see which bound we need. So how we can use the fact that the number of errors is small? So somehow we need to connect the number of errors with our multiplicities. So we need to show how we can prove that this is polynomial is 0. First of all, we know what is the degree of this polynomial. The degree of r x p of x is equal actually to k degree of r, because we know that p of x has degree k, at most k. And so this is a k degree of r. And we know that this is less than d. So somehow we need to ensure that if the number of errors is small, then that polynomial has many root counting multiplicities. Many means at least d. So instead of proving this, we can show that this polynomial has more roots counting multiplicity than its degree, because then by algebraic theorem, we know that it is actually 0. So how many roots that polynomial must have? First of all, we know that if p of certain xi is equal to certain yj, then xi yj is a root of R with multiplicity sorry, I didn't mean that. I meant something else. Then xi and not that pair. Then xi is a root of R of x, p of x, with multiplicity a ij. And this is because we have chosen R so that each pair f xi yj is its root with multiplicity a ij. So if it happens that p, the graph of p passes through the point xi yj, then xi will be the root of that univariate polynomial of multiplicity a of ij. So we have seen it once when we considered when we considered an algorithm to decode Ritzel, to decode Ritzel-Lamont code. So now, what do we know? If we still need to connect somehow the number of errors to the total number of so the number of roots, let's write trivial thing. So the number of roots of R of x, p of x is then at least the sum of all aij such that p of xi equal to yj. This follows from the previous line. So we need to count how much is that number. Okay. So what do we know? So the number of errors introduced is equal to, so write the following picture here. So this is one block in the Adamar in the code. So call it, so here the genuine, here is the genuine block. So the code of p of xi. And now this is the corrupted thing. And the total number of errors is actually equal to, oh, let's write it here. So the total number of errors is equal to the sum of the distances between the I and P of xi over, and the sum is over all the I in the field. Sorry, here we need to write the code of P of xi. Now, if P of xi is equal to yi, so assume that now P of xi is equal to yi, then this is our B of what is called Bij, yj, sorry. So recall how we defined it, so B of ij is the distance between what we receive and the code of yj. If yj is equal to P of xi, this is just one term from our sum. So the number of rules is at least, the number of errors is equal, can be just rewritten as the sum of B ij, where the sum is over all I and j such that P of xi is equal to yj. So we consider all points on the plane on the graph of our polynomial and sum up all bij's. Now we know that let's rewrite it as follows. 2 to the m minus 2 times the number of errors is equal to the sum of 2 to the m minus 2 bj oh, not this way. 2 to the m minus 2 to the bj, where the sum is over all ij such that the P of xi is equal to yj. And now recall how we defined our aij. We defined aij equal to 2 to the m minus minus 2, let's recall the definition, 2 to the m minus 2 bij if positive and otherwise negative. So we know that actually in any case 2 to the m minus 2 bij is less than our multiplicity. So because our multiplicity is either 0 when this is negative or just equal to this guy. And so if we sum up this, so we can replace 2 to the m minus bij by aj and obtain a larger value. So let's see. Where's I'm sorry. So let's erase this. So what I want to say is that we can connect the number of errors and the degree in the following way. So the number of roots is that guy. That is at least, so let's recall this. This is at least the same sum, but here we can replace aij by 2 to the m minus 2bij. So now так, давайте сделаем перерыв. Я соберусь с мыслями, а то что-то я потерялся. Значит, через 5 минут продолжим. Так, ну давайте продолжать. Зря потерялся. Здесь на самом деле совсем просто. Давайте я вот эту часть договорю по-русски, чтобы было проще. Значит, смотрите, вот это вот в этой сумме, которая у нас есть нижняя оценка для количества корней, она, по существу, два слагаемых, 2 в степени m суммируется 2 в степени m раз, потому что количество точек на графике 2 в степени m. Значит, мы получаем, что это равно 2 в степени m на 2 в степени m минус сумма минус 2 умножить на сумму всех b и g, ну, соответствующих графику, то есть по всем точкам и по всем и g, таким, что p от x и равно y(g). А эта сумма у нас по условию как раз есть количество ошибок. Значит, получается 2 в степени 2m минус количество ошибок. Ну и таким образом, значит, если окажется, что эта сумма больше либо равна, чем d, чем степень нашего многочлена, то все будет для нас хорошо. Мы получим, что r от x p от x равно нулю. Таким образом, нам нужно, чтобы удвоенное количество ошибок было меньше, чем 2 в степени 2m минус d. Ну, 2 в степени 2m – это длина кодовых слов. Значит, вот здесь вот в условии теоремы нужно просто написать, мы это вот пропустили, что удвоенное количество ошибок не превосходит значит, 2 в степени 2m длину кодовых слов минус d. Ну, а просто, если количество ошибок, то пополам. Вот. Вот если выполнено такое неравенство, то тогда все хорошо. Okay, now I switch to English. And this lemma guarantees that if this inequality is fulfilled, we are in good shape. What does it mean? We know that P of x is a root of this. And we know that this implies, actually, that R is divisible by y minus P of x. And so we can find, once we have R, we can factor it using an efficient factoring algorithm and just single out all the factors of this type. These are irreducible factors. And the number of such factors will be at most the degree of R in y variable, which is at most d over k. So by our lemma, so let's summarize. On the first step, we find all irreducible factors of R, then take those of them of the form y minus a polynomial p prime, call it p prime of x, and put all such p primes in the list. So we will obtain a size of the list will be d, the degree of R, divided by k, which is equal d over epsilon 2 to the m, because k is epsilon 2 to the m. So finally, we obtain our algorithm. We have described our algorithm. So our d is square root of k, which is epsilon 2 to the m, of the sum of aij plus 1 over all ij. So ij ranges from 1 to 2 to the m. So this is a large sum. And the size of the list is equal to d over k. So the size of the list will be that sum. So list size will be this sum over epsilon 2 to the m. So this is what we obtain, but still we need to upper bound this guy, because to prove the theorem in the form we have stated, so we have stated that the size of the list is that much and the number of errors will be that much. By the way, we forgot to say how many errors we correct. So everything assuming that the number of errors is less than what? Than 2 to the m minus d over 2. Is less than... Ага, меня выбросило. Сейчас, слышно меня теперь?
Да, слышно.
Да, слышно.
Да-да-да.
Так, значит, что там последнее вы видели? Ой. Так, и на доске уже ничего нету. Ну хорошо, я напомню. Вот у нас d мы полагаем корень из эпсилон 2 в степени n сумма по всем ij, ij на ij плюс 1. Так, размер списка. Там size of the list. And assumption, что the number of errors must be smaller than 2 to the 2m minus d over 2. So, first of all, we need a lemma that upper bounds this. So we want to show, we will show actually that this sum, so actually we just rewrite this sum. Is at most, let me see. I guess 2 to the 3m plus 2 to the 2.5m. So almost, I mean, this is the bound for the first term, 2 to the 3m, and this is the bound for the second term. And so more or less, this is approximately, when m is large, 2 to the 3m. And so we obtain here that our d is approximately equal to square root of epsilon. Da epsilon times 2 to the 2m, because we have here 2 to the m times 2 to the 3m. So in total, square root of epsilon 2 to the 4m. And so the size of the list is then 1 over square root of epsilon 2 to the m. So this is worse than in Johnson bound. In Johnson bound, we had here 2 times 2 to the m. But still, this is for fixed epsilon, order of 2 to the m. So linear in the 2 to the 2m, linear in the block length. And the number of errors is 2 to the m minus square root of 2 to the m over 2 to the 2m minus square root of epsilon times 2 to the m over 2. So this is, the number of errors is approximately, this is approximate equality, this one, equality. Almost the same as, so this is the block length n times 1 minus square root of epsilon over 2. So almost the same number of errors as in the Johnson bound. But the advantage is that our algorithm is polynomial time, and the Johnson bound is just a purely combinatorial thing. So we need to prove now our lemma. So first, let's upper bound the first term. We can rewrite it as follows: the sum over all i's, the sum over all j's of aij squared. Now, this sum has, the outer sum has 2 to the m terms. So for each I, we will upper bound the sum over j's, using the fact that actually it was defined as a difference, as the number of differences between a certain string and different code words. So recall how we defined our aij. First of all, aij were either all of them were at least 2 to the m minus the difference, minus what we call bij, 2 times bij, which is, so aij was defined as either 0 if this is negative, if not positive, or this one. So we have this bound, and this guy is equal, bij is equal to the distance between what? Between the code word encoding yj and the ith block we have received from the channel. So, and now we will assume that all our code words, everything is the sequence of plus minus ones. So instead of 0 and 1s as alphabet symbol, we will use plus minus 1s. And then we can rewrite this thing, as we did several times before, as the inner product of these two strings, zi, assuming plus minus 1 notation and code of this one. So, now we know that this sum is at least the sum of square. So let's rewrite it now. So the sum, we have fixed fixed I, and so this sum over j, aij squared, is at least the sum of the inner product of zi, which is fixed, and here we sum up over all code words of Adamar code. So Cj is a code word. Now we know that all the code words are pairwise orthogonal. So let's normalize them. So the inner product of each code word and also the inner square of each code word and also inner square of the I is 2 to the m, because these are strings of 2 to the m plus minus ones. But let's normalize all the code words. I forgot to square it, and let's normalize them, dividing by their square root of their norm. So by their norm, which is 2 to the m over 2, and also multiply by 2 to the m. So, and now we can use the Parseval inequality, because now Cj over normalized Cj are pairwise orthogonal, and all they have norm 1. And so by Parseval inequality, oh, I'm sorry, we have here the bound in the other direction. That much, because this actually we do not need this inequality. We know that otherwise either this is 0 or this is equal to this. And so when we square all the aij's, their sum is at most the sum of bij squared trivially. So this is the sum of bij squared, and by Parseval inequality, we obtain that this sum is at most the square of the I, the inner square, which is 2 to the m. So we obtain 2 to the 2m. And this is for fixed I. And when we sum up over all i's of this, we obtain 2 to the m times this upper bound, 2 to the 2m. So we obtain 2 to the 3m. So this was the bound for this one. So this is at most 2 to the 3m. Now we need to upper bound this one. And this will be done as follows. So again, fix I. The sum of all aij's can be fix I. Then the sum of all this may be upper bounded using the inequality between arithmetic mean. So this is the arithmetic mean of all aij's when I is fixed, and quadratic mean. And the quadratic mean is the square root of the sum of all aij squared over again 2 to the m. So this is at most 2 to the m, as we have seen. 2 to the m. So we obtain two to the 2m over 2 to the m, which is 2 to the m over 2. And hence the sum of this the sum of aij's for fixed I is at most 2 to the 1.5 m. And then when we sum over all ij's, we obtain 2 to the 2.5 m as we have seen. So this sum, the second sum, is at most 2 to the m times 2 to the 1.5 equal to 2 to the 2.5 m. And so we obtain indeed those bound we claimed. So this is at most 2 to the 3m, about 2 to the 3m, which implies all the good consequences. Ну вот, вроде я закончил алгоритмы, доказательства. Есть ли вопросы?
А почему он полиномиальный? Или тут понятно?
Ну, понимаете, он полиномиальный в каком параметре? n у нас есть экспонента, длина. Значит, смотрите, все, что мы делаем, мы там рисуем табличку размера 2 в степени m на 2 в степени. И все это линейно по n, по длине блок, по длине кодовых слов. Значит, мы рисуем табличку, составляем эти самые, вот эти числа. Значит, составляем систему уравнений. И в этой системе полиномиальная от n, количество уравнений, количество неизвестных, там тоже полиномиально по m.
Понятно, да, хорошо.
Вот. Ну, алгоритм Гаусса, он полиномиальный. Алгоритм факторизации полиномов, он полиномиальный. Все, что мы используем, это полиномиально от n. От m, конечно, экспоненциально. Вот, значит, какой организационный вопрос вы хотели обсудить?
Вот смотрите, вы внесли наш курс в список курсов, но только, наверное, стоит его внести как ЕНС на английском, потому что это разная градация. ЕНС просто и ЕНС на английском.
То есть внесли, но неправильно внесли. Ну, хорошо, я скажу этому нашему ученому секретарю, чтобы он внес как ЕНС на английском.
Хорошо, спасибо большое.
Теперь, эти самые... Я специально приду в МГУ в 11 часов в понедельник. И желающие могут передать мне зачетки. Я буду на кафедре сидеть, на нашей кафедре матлогики. Но я недолго там буду сидеть, там, я не знаю, полчаса. Значит, 11:00 в понедельник. Запомнили?
Но у нас зачетки в учебной части, скорее
Да.
всего.
А, все зачетки в учебной части, у нас их нет, и мы вряд ли можем ходить особо в МГУ.
То есть это бессмысленно, вы не сможете мне их передать. Ну ладно,
Да.
тогда это мы обсудим потом, когда они у вас вообще появятся. Хорошо, я понял. Тогда, ну что я сделаю? Я проверю ваше последнее задание, которое вы мне уже все прислали, выставлю в таблице тесты, и результаты тестов я еще не все внес, и оценки. И, ну, и все увидят, у кого что получается. Ну, наверное, у всех зачет более-менее, кто сейчас здесь слушает. Мне так кажется. Вот. А ведомость я уж сам проставлю, я надеюсь, в это просто в понедельник. А в зачетке тогда это отдельно будем обсуждать. Ну, давайте я последний тест вам дам, и мы уж попрощаемся. Так. Так, ну он очень простой, поэтому давайте я лимит времени все-таки в 10 минут установлю, чтобы не ждать. Значит, 14:28 закончим. Там всего 3 задачи.
Сколько там времени осталось, не подскажете?
Так, все, значит, заканчиваем прием. По-моему, все уже, собственно, отослали. Так, ну ладно, до свидания, всего хорошего. Еще встретимся, когда я в зачетке буду представлять.
Извините, а вы обратный отсчет не сделали, и я не...
Обратный отчет. Ну,
Да,
хорошо.
вы обычно...
Тоже не
Посылайте.
успела.
За
Да,
10
кстати,
секунд
я
вы
тоже
можете все
не
послать.
успел.
10, 9, 8.
Ее снова заполнить надо.
Да, там, короче,
Она же сбросилась теперь.
да, погодите примерно.
Сколько вам
Подождите.
нужно времени?
Ну,
чтобы
хотя бы секунд 30.
Да.
Хорошо. Даю вам 30 секунд. Так, ну, по-моему, все уже послали. Есть кто еще не послал? Ага, нету. Ну, все тогда. Тогда все. Хорошо. Тогда до свидания всем. Встретимся еще, когда зачетки.
До свидания.
Мгм.